Hello and welcome to the 13th and final presentation in the Treesearch and WWSC Science Center virtual conference series. This conference series was initiated to contribute to the scientific discussion in a time where conferences and workshops have been cancelled due to the COVID-19 pandemic. The full program and previous speakers can be found at the Treesearch webpage. My name is Josephine Illegård, and today I have the pleasure to present today's speaker, Merima Hasani, who will present Putting Together the Puzzle of Cellulose Interactions in Aqueous Alkaline Solutions, from cations to carbon dioxide. Merima is Associate Professor at Forest Product and Chemical Engineering at Chalmers. And you in the audience can interact and ask questions or comment via the YouTube chat function. And you need to be logged in to YouTube to do that. And any questions will be answered after the presentation. And with that, I hand over to Merima.
Thank you, Josephine. Now I will just share my screen. Yeah, okay. Now you can see it, hopefully. Okay, so thank you for this introduction, and thank you for inviting me to this seminar series. As you said, I work at the Forest Products and Chemical Engineering, and I work with different aspects of cellulose chemistry and biorefinery. And today I will talk about cellulose solutions in aqueous alkali. And these cellulose solutions in aqueous alkali, they have been around for almost as long as cellulose chemistry itself. And in spite of that, they are in a way still a mystery. And I would say that our understanding of these, let's say, scientifically important, but also industrially attractive systems is still surprisingly limited. And of course, one of the most intriguing aspects is their instability, or actually tendency of the dissolved cellulose chains to reassociate and aggregate. And of course, considering transition between two states here, between the native cellulose 1 and the more stable cellulose 2 or regenerated cellulose, these solutions can be seen only as a transition states, leaving always inevitably to the most stable cellulose 2. But the properties and the lifetime of these transition states will be very different depending on the outer conditions. And the main question for us here is, of course, how can we act within this rather narrow dissolution window? How can we affect the properties or control the properties of cellulose in terms of stability, in terms of reactivity, chain conformation, supramolecular organization, and so on. And of course, addressing these questions has to start by gaining a proper understanding for the most fundamental interactions governing the properties of this dissolved state. And one of these very fundamental questions that we have been very much intrigued by is the role of the cation in these solutions, because role of the hydroxide anion in these alkaline solutions is rather easily rationalized, as it has to somehow involve strong interaction with cellulose hydroxyls, whether through complete deprotonation or strong hydrogen bonding. But the role of the cation is far from well understood, and I will share today some glimpse from that search with you. And of course, understanding the role of the cation is also closely related to introducing other components or other structures that would be capable of improving stability of this dissolved state. And I'm, of course, talking about the introduction of different additives to this system. They are frequently used in these systems, but are not sufficiently understood. So I will also very briefly touch upon the role of the additives as well, urea in particular. And finally, as another puzzle piece in trying to understand molecular interactions in these systems, I will also talk about a rather new dimension, rather recently discovered dimension of the system, and that's their interactions with carbon dioxide. But let's start with the pink puzzle piece and the role of the cation. And of course, cation properties will affect a number of interactions here. For instance, dissociation of the ion pair, interaction with water, which in turn will, of course, affect interactions with cellulose. And here on the left side, you can see two different types of cations interacting with water. The small cations, so-called structure-making cations with high charge density that as such will form strong hydrogen bonds with water. And the larger so-called structure breaking cations with lower charge density, that such will quite loosely interact with water and also exclude some of the water molecules from these interactions. And of course, some of these cations will not work at all as cellulose solvents, not even when combined with good cations, as you can see on the picture here. But our approach here was to focus on the good ones, to focus on the good cations, study their cellulose solutions, and then learn from the comparison. Here you can see three cations, or actually their hydroxide bases that we selected to study. All of them work as cellulose solvents, but their cellulose solutions will behave differently. And most of all, we wanted to find out about the stability of their cellulose solutions. So, and in that case, of course, studying flow properties at different temperature can give us a pretty good information. So what you will now see for each of these is how viscosity is changed as a function of shear rate at different temperatures. And for sodium hydroxide, not surprisingly, we could see a substantial increase in viscosity at higher temperatures, which of course indicates extensive or significant aggregation. And also at lower temperatures, as you can see here, we could observe some signs of network formation. On the other hand, for this quaternary ammonium hydroxide, the picture, or the quaternary tetramethyl ammonium hydroxide, I should say, the picture was completely different. And also for this third base here, 3-methyl benzyl ammonium hydroxide, that I will in continuation call tritone for simplicity. So as you can see, both of these quaternary ammonium bases or hydroxides showed almost completely Newtonian behavior over the whole temperature range without any significant signs of aggregation. And these findings inspired us to try or to consider using these rather powerful quaternary ammonium hydroxides as additives to the rather poor but still very widely used sodium hydroxide solutions. So we ended up trying to combine them in different proportions and finally decided to combine them in proportion 50-50. And this is what we could observe. As you can see here, even though we could obtain some improvement compared to the pure sodium hydroxide, it seems that so the presence of sodium hydroxide always promotes aggregation at higher temperatures, even though when combined with rather powerful quaternary ammonium bases. Interestingly, the addition of urea improved this stability a bit, especially for the sodium hydroxide containing bases, but we couldn't really see any large effects or any effects at all in some cases for these already well stabilized quaternary ammonium hydroxides. A big surprise, or I should say actually disappointment in this case, was this combination sodium hydroxide tritone, that in spite of excellent properties of Triton, didn't really manage to stabilize cellulose when combined with sodium hydroxide. And not even the presence of urea could really help in this case, as you can see here. On the other hand, combination sodium hydroxide tetramethylammonium hydroxide showed only shear thinning behavior at the higher temperatures, but no obvious signs of aggregation. And in combination with urea, this system was actually behaving as a Newtonian solution. This actually shows that combining bases is far from trivial, because the base pair or the base combination should be really selected with great care, because combining them can be far from the success story, as you see here. We will get back to urea later on, but for now, let's dwell a bit more on these different solutions, and let's take a look at their dissolution capacity. Very much in line with what we just saw on flow properties, we could see that the solution capacity actually increased in this series. As you can see here, it increased from sodium hydroxide over tetramethylammonium hydroxide to Triton. And again, not surprisingly, based on what we just saw on the flow properties, the solution capacity of Triton was significantly reduced when combined with sodium hydroxide, even though we obtained a slightly better result than for the pure sodium hydroxide. But very interesting surprise, or I should say very pleasant surprise here, was actually the combination sodium hydroxide tetramethylammonium hydroxide, where the solution capacity for the combination actually significantly exceeded the dissolution capacity of the individual bases, as you can see here. So obviously here we had some synergetic effect that would contribute to increased dissolution capacity. And of course, all these findings raised a number of questions. For instance, why are these quaternary ammonium hydroxides better stabilizers for cellulose than sodium hydroxide? Why is their effect not appreciably affected by urea? What about temperature effect? And why actually do some combinations work better than the others? And when trying to understand these things on the level of molecular interactions, we turn to the so-called solvatochromic dyes, or actually structures or compounds that are capable of changing their interaction with light when subjected to certain type of interactions. One commonly used such structure is this one, that, as you can tell by its structure, will readily interact with the protons or proton donating structures, and will as such measure or probe the hydrogen donor ability of the solvent. We also use we also use this structure that will, as you can tell, participate in hydrogen bonding as a hydrogen donor, which means that it will actually measure the hydrogen acceptor ability of the solvent. And then finally, we also use these two structures that can give information on interaction capacity of the solvent through dispersion forces. And of course, as we here deal with the highly alkaline solutions, the hydrogen acceptor ability or basicity is what is easiest to understand here. So simply information that we could get by measuring interactions with this probe. And in our series, we could actually observe increased basicity or increased hydrogen acceptor ability. And this increased basicity of the more hydrophobic quaternary ammonium bases is commonly in literature attributed to the higher dissociation of the ion pair in these bases, which would basically mean that that the hydroxide anion is more mobile and more free to act as a strong base in this case. But very surprisingly, also actually the hydrogen donor ability and acidity increased in this series, as you can see here. And that is not as easily rationalized, as these bases actually don't contain any easily donated protons. But we should remember here that these probes that you just saw, they actually measure or can sense the overall properties of the solvent, including the properties of the surrounding water. So this increased acidity in this series is actually closely related to the acidity of the surrounding water, because it is well known that water surrounding more hydrophobic structures will to a greater extent be excluded from the, let's say, normal hydrogen bonding, and will as such contain higher proportion of the water molecules that are more prone to donate hydrogens, and that will be more acidic. So that actually means that this parameter, acidity parameter, increasing in this series carries an important but indirect information on hydrophobicity of these cations. And overall, we can say that the increased basicity is of course beneficial, but also increased acidity or increased actually ability to interact with the less hydrated regions in cellulose. I should also say that we, for these bases, measured also this interaction through dispersive or dispersion forces, but here we couldn't really get any conclusive results. As you can see here, slight difference between these two, but and increase in the case of Triton, but we couldn't really be conclusive on these results. But what about combinations? Well, actually, as you can see on the combination tetramethyl ammonium hydroxide, sodium hydroxide, these parameters, we obtain parameters that are something in between the values for the individual bases, which basically mean that these couldn't really help us explain increased dissolution capacity of this combination compared to the individual bases. And these parameters were not helpful very much either in the case of the combination sodium hydroxide Triton. So altogether, as these considerations of hydrogen donor and hydrogen acceptor ability couldn't really give us any deeper understanding behind the differences in these two combinations, we turn to differential scanning calorimetry, trying to understand the structure of these different solutions, because normally differential scanning calorimetry can show variations in hydrated structures present in these solutions by sensing their melting enthalpies, and can also help us identify those structures that are actually affected by cellulose or that are involved in interactions with cellulose. For instance, this is what you normally can observe for cellulose dissolved in sodium hydroxide solutions. What you see here, and this is actually the melting enthalpy corresponding to the amount of free sodium hydroxide hydrates in these solutions. And these hydrates have been commonly or have been identified as those actively interacting with cellulose and stabilizing cellulose in these solutions. And of course, as we increase cellulose concentration here, the amount of free sodium hydroxide hydrates will decrease as they will increasingly interact with cellulose. And finally, when we reach the saturation point with cellulose in the solution, we will not be able to detect any more free sodium hydroxide hydrates. And when combined with the tetramethyl ammonium hydroxide, like here, we actually still can observe the same melting enthalpy peak for sodium hydroxide hydrates, which is what you see here. But as we here deal with a combination of bases, of course, we can observe also another type of hydrates, those coming from the tetramethyl ammonium hydroxide. And very interestingly, in this case, actually, when we increase cellulose concentration, these peaks will decrease, or the amount of free tetramethyl ammonium hydroxide hydrates will actually decrease, meaning that, or indicating that these are probably the hydrates that are favored by cellulose. While at the same time, the amount of free sodium hydroxide hydrates will slightly increase, which might indicate that they are simultaneously, to a certain extent, excluded from cellulose interactions. On the other hand, when combining sodium hydroxide with triton, in this case, we could observe only one signal, or a signal for only one melting enthalpy, so probably only one structure, and no signs of individual hydrates of these two bases. So no signs of hydrates that would normally otherwise be formed in a single base solutions. So this might actually indicate that in this case, these two bases actually disturb each other's hydration, or disturb formation of these their individual hydrates that they would normally form when in individual or single base solutions. And this can give us a hint, or at least provide one possible explanation behind the very different behavior of these combinations. Because based on this, it seems that hydration of the bases in a combination is also an important factor. Or I should say, it's important that appropriate hydrated structures can be formed, structures that will then be active in cellulose dissolution. So at least we could get one hint here by with the help of differential scanning calorimetry. We also devoted a bit more, this is just what you see here, that the amount of the free quaternary sodium hydroxide will decrease at the same time as the free sodium hydroxide will increase when we increase cellulose concentration, which again indicates that these hydrates are probably preferred by cellulose. And we, of course, devoted some more attention to this rather successful combination of tetramethyl ammonium hydroxide with sodium hydroxide. So we measured the intrinsic viscosity of dilute cellulose solutions in the combination, and could actually observe a slightly higher value than the intrinsic viscosity of the single base solutions with cellulose. And that, of course, might indicate that cellulose chains are slightly more expanded or slightly better solvated in this combination of bases. But as these differences are actually rather small in this case, we can probably assume that we here deal with a similar dissolution mechanism and similar stabilization mechanism in all three cases. So what we could say so far altogether about this interesting combination, sodium hydroxide, tetramethyl ammonium hydroxide, is that the cellulose chains seem to be slightly more solvated and expanded in this base combination solution. We could observe significantly higher dissolution capacity. And very interestingly, we could also observe better stability over time or postponed gelation in this case. And that's what you can see here. Because what you see here is actually time-resolved rheology, or more specifically, storage and loss modulus as a function of time, with their crossover point as an estimate of starting gelation point. And indeed, as you can see, the combination of base or combining bases in these solutions indeed postpones gelation and improves stability over time. Because we measured here at 3 different temperatures, 15, 25, and 35 degrees. And for each of these temperatures, actually the single base solutions already gelled before we started measuring, but a combination of bases managed to postpone gelation by approximately 15 minutes here, 11 minutes here, and let's say 3 minutes here. But what is very interesting also is that this combination of tetramethyl ammonium hydroxide and sodium hydroxide doesn't seem to be that powerful anymore when the temperature is raised to approximately 35 degrees, which probably means that we, in this case, and especially for higher temperatures, would need a different base, a different cation that would possibly provide stronger stabilization through, let's say, less temperature sensitive dispersion forces. Because actually both tetramethyl ammonium hydroxide and sodium hydroxide are so-called cosmotropic compounds, which means that they will form strong hydrogen bonds in aqueous solutions. So they will mainly act through strong hydrogen bonding, and that will of course be weakened at higher temperatures. So for improved stability at higher temperatures, it's possible that we might need another cation, or cation with more extensive van der Waals interactions. But combining that cation with the sodium hydroxide might be very tricky, as we just saw in example with the Triton. Another interesting or another important thing to consider when analyzing these 3 graphs is actually, I would say, a need to understand and interpret this gelation in terms of 2 parameters, both temperature and time. Because as you can see here very clearly, this gelation or aggregation is actually dependent on both temperature and time. And temperature dependence is what I've talked about now quite a lot. And what we could say about that now is that it seems like that enhanced stabilization through dispersion interactions is beneficial for stabilization at higher temperatures. And again, that is quite easily rationalized as stabilization through hydrogen bonding will be, of course, strongly weakened at higher temperatures. But what about stability over time? How do we explain that this combination of sodium hydroxide with tetramethyl ammonium hydroxide will postpone gelation compared to the solutions of individual bases? Well, we work actually currently on that, and it is possible that when 2 bases are combined, that they will actually lead to formation of a different solid state, or a solid state that is less stabilized compared to the solid state that we can obtain when having only one of these bases in solution. Because stability of the solid state that will be formed after aggregation or gelation will of course be an important factor determining the lifetime or the stability of the dissolved state. And this is actually the hypothesis that in a way was brought up earlier by Olson et al. pointing out stability of the cellulose 2 as the main driving force in this transition. But of course, depending on the composition we have here, this transition will go through very different intermediate states, leading finally to the stabilized cellulose 2. This intermediate might be very different depending on the combination of bases or base composition that we will have over here. And this hypothesis is what we investigate right now, focusing very much on the composition of this state and also trying to identify different hydrated intermediates. So with that, I will stop with the cation puzzle piece and move on to another puzzle piece, and that is carbon dioxide one. Because as I mentioned in the beginning, when discussing molecular interactions of these systems, there is actually another dimension and another component that should be taken into account and that has been quite overlooked for a long time. And that is interaction with carbon dioxide and also with the different carbonate species that are formed as a consequence of that chemistry. And that is actually a dimension of these systems that we discovered quite unintentionally, because whenever we were coagulating cellulose that was dissolved in these systems, predominantly in sodium hydroxide systems, whenever we were coagulating it with a water-free antisolvent, for instance, water-free ethanol, and a new FTIR signal could be observed in this coagulated cellulose, a signal at 1592 that you see here, and that is actually commonly attributed to organic carbonates, or more specifically to alkyl carbonate salts when involved in extensive hydrogen bonding. And the only structure that in this case could possibly contribute to formation of an organic carbonate would of course be carbon dioxide from air, whether as a molecule or as a converted to carbonate ion in these highly alkaline systems. Interestingly, whenever we used water or water-containing antisolvent, on the other hand, this signal would be gone. And that is very much in line with what is already known about stability of these structures. It is well known that they are sensitive to water and they are easily hydrolyzed off by water. And actually already in the early 1920s, it was well known that this type of compounds should be worked up only with water-free solvents, for instance, water-free alcohols. These carbonates could be observed also on the NMR, or more specifically, actually, what we could observe were their further interactions with NMR solvents. What you can see here is NMR for the reference cellulose, which means cellulose that has actually never been dissolved in sodium hydroxide, but just dissolved in the NMR solvent, which in this case was DMSO with IMIMAC. This area is actually area where we expect to see carbonate signals, but for reference cellulose, we could only see the signature of the NMR solvent and nothing else. But for cellulose that has been dissolved in the sodium hydroxide solution and then coagulated with water-free ethanol, we could actually observe 3 new peaks. And these new signals originate actually from the carbonate, organic carbonate, and probably cellulose carbonate being transferred further to the NMR solvent, in this case, imidazolium part of the solvent, giving rise to a new imidazolium peak. And I should mention that this is actually a commonly observed behavior of the organic carbonates when in presence of the imidazolium structures. But also partly these signals originate from the carbonate being hydrolyzed off by the residual water in the NMR solvent, giving rise to bicarbonate and carbonate signals. We could observe new signals also in the cellulose area, as you can see here. And interestingly, again, when using water as a coagulant or as anti-solvent, these structures would be hydrolyzed off and we wouldn't be able to observe any signals in the carbonate area and no signals in the cellulose area either, which indeed indicates that we, in this case, deal with water-sensitive structures that will easily be hydrolyzed off in the presence of water. Understanding and interpreting these signals in the cellulose area wasn't really easy, but supported by extensive NMR analysis and also to a certain extent molecular modeling, we could get indication that these signals actually originate from the residual carbonate that remained in the cellulose structure after dissolution in the NMR solvent. So carbonate that hasn't been transferred further to the NMR solvent, but remained in cellulose, possibly bridging over to different positions in cellulose, which also might be the reason why it actually survived dissolution in the NMR solvent. But we need a bit more work here to be conclusive and to be sure about that. But on the other hand, a number of our studies pointed out that freshly added carbon dioxide could interact very specifically with the cellulose or carbohydrate that was already dissolved and activated in the highly alkaline system. Because what we could observe was that, for instance, freshly added carbon dioxide introduced to the system containing already dissolved and activated carbohydrate. In this case, it is cellulose analog methyl glucose, could actually displace the signals of the carbohydrate significantly more compared to the addition of the same amount of carbon dioxide to the system, but prior to addition of the carbohydrate. So in this case, we could actually assume that carbohydrate that is already dissolved would have a chance of interacting with the molecular carbon dioxide before it actually gets converted to the carbonate ion. But in this case, where carbon dioxide is added to the system prior to dissolution of carbohydrate, we can assume that the only species that is available for interaction with the carbohydrate is carbonate ion. And as we observed significantly more replaced NMR signals or NMR shifts, in this case, it of course indicated very specific interaction between the dissolved carbohydrate and freshly added carbon dioxide. And very interestingly, in this case, we could also introduce significantly more carbon dioxide into the system compared to this case. And that's what you can see here. And very interestingly, this significantly higher incorporation of the carbon dioxide into the system, which corresponds to this green line, didn't seem to be actually accompanied by any additional reduction of the pH value compared to this red line, which corresponds to this case. So it seemed like we, in this case, where carbon dioxide was introduced to the system already containing dissolved carbohydrate, we could pump in about 4 times more carbon dioxide and also stabilizing in that system without consuming any additional alkali, any additional base compared to this red case. And based on all these findings, and also supported by early carbohydrate literature reporting on the formation of glucose carbonates under similar conditions, we could finally propose the following mechanism for the carbon dioxide interaction with these systems. It would be initiated by a nucleophilic attack of the dissolved and deprotonated cellulose on the incoming molecular carbon dioxide, leading to formation of a transient cellulose carbonate intermediate that would be readily hydrolyzed off by water, leading to formation of the carbonate ion. And this route might be the secret behind this significant incorporation of the carbon dioxide into these systems without any appreciable consumption of base, because here the mechanism goes through cellulose carbonate intermediate, not consuming hydroxide ions. And this carbonate ion is actually very interesting, as it actually behaves rather differently compared to the normal carbonates. And by normal carbonates, I mean carbonates that you see here that are normally introduced by base-mediated conversion of the carbon dioxide. But this carbonate will actually show displacement of the NMR shifts upfields compared to this normal carbonate in the system. And the introduction of this carbonate is also associated with the change of the NMR signature of the carbohydrate, or more specifically, it's associated with the change of the coupling constant here, which is informative of the orientation of the primary alcohol. So not only that this carbonate is introduced to the system through reaction with the carbohydrate, cellulose for instance, but it also seems to be affected by carbohydrate, and which might then mean that they might be in close proximity in these solutions. And indeed, when we, in an NMR experiment, saturated the signal of the carbonate ion and then measured its influence on the cellulose signals, we could indeed observe that all cellulose signals were actually affected by the magnetization of or by the saturation of the carbonate signal, which again might indicate that they are indeed close to each other in these solutions. So it's possible that stabilization of this carbonate by cellulose, as they seem to be close to each other, might be one of the reasons why we actually can introduce so large amounts of carbon dioxide and carbonate ions into the system and still keep it stable. Okay, so I will stop with this part, and as I promised in the beginning, I will now very, very briefly go back to the urea or additives puzzle piece, but in a slightly different way, having in mind what we just saw about carbon dioxide chemistry of the system. So based on what I just showed you, we can tell that the signature of the carbon dioxide interactions with the system can be summarized like this. It is the larger displacement of the carbohydrate NMR shifts when interacting with freshly added carbon dioxide compared to the addition of compared to the interaction of the interaction with the carbonate ion. It is also close proximity of the formed carbonate with cellulose, and also changes in the coupling constants probably related to the orientation of the primary alcohol. So that's a signature of carbon dioxide interference with the system. And very interestingly, in the presence of urea, none of these things could be actually observed. no displacement of the NMR shifts, no proximity of the carbonate regarding cellulose, and no changes in the coupling constants that could be related to the change in orientation of the primary alcohol. So obviously, urea interferes strongly with the carbon dioxide chemistry of the system, and we still don't really understand how. This might indicate that carbon dioxide urea interactions are preferred over interactions with cellulose. It might be that we have a shielding effects of urea in these systems, or both, or something else. We will continue this work anyhow. So with that said, let's take a look at what puzzle pieces can we put together then today. Well, what we said about cations is that, yes, hydrophobicity and stabilization through dispersion forces is definitely beneficial, especially for temperature stability. But combining them might be very tricky. Carbon dioxide will interact with this system through formation of cellulose carbonate intermediate. And it is also possible that carbonate formed through this route is somehow associated to cellulose, or let's see, we could see that it is in close proximity to cellulose in these solutions. And urea didn't show any appreciable effect on the already well-stabilized quaternary ammonium hydroxide solutions, but it showed a significant interference with the carbon dioxide interactions. And with that, I would like to thank all the people that have been working with us on these questions. I would like to thank our financiers, our collaboration networks, and most of all, I would like to thank my fantastic PhD students that have done all the work that I have presented. Beatrice, who is working on the cation and stability track. Maria, that was working on carbon dioxide dimension of the system. And Shirin, that is currently struggling to turn these solutions in the well-functioning derivatization media as well. And I would also, of course, like to thank all of you for listening.
So thank you very much, Merima, for showing us the puzzle pieces. Are you close to solving the puzzle, or what you say? Or?
Oh, no. We just discovered new puzzle pieces to be revealed.
So now we're open for questions from you in the audience. So take the chance to ask Merima some questions. And this is the last presentation in this seminar series. As I said at the beginning, you can find all the previous presentations and this presentation, of course, at the Treesearch YouTube channel and at the conference webpage. So let's see if we have any questions.
If you don't have any questions now, you are, of course, welcome to email me.
We have a comment, at least. Amadresa, sorry for the pronunciation, say thank you for the presentation.
Thank you for listening.
So no further questions, and you can find Merima's email at Chalmers webpage, of course, if you have more questions, I guess. So I say thank you very much, Merima. Very interesting presentation. And thank you to all who have been listening. So thank you when we close this this seminar and the whole Treesearch and WWSC Center virtual conference series. Thank you for following us.